Thanks for inviting me for this interesting conference. So what I will try to talk about today is about counter-diabatic driving in quantum many-body systems. And so I realized that for probably most people in this conference, it contains a lot of things they're either unfamiliar with, maybe less interested in. And so it's about quantum many-body systems, so I'm mostly interested in, like, say, strongly correlated systems, although most of the things I will talk about in this talk will be still about simple systems, because I want to basically introduce this concept of counter-diabatic driving. And so the work has been done in collaboration with Anatoly Polkovnikov at BU, so most of the things I will talk about are also due to him. So big part of this conference has been concerned with, let's say, improving figures of merit of like certain devices that we can use to generate work, right, or to transport heat. And so we all know, right, from any undergraduate textbook that you obviously cannot make any device that works with a higher efficiency than the Carnot efficiency. But as we all sort of are familiar with that, yeah, a usual device that works at Carnot efficiency generates no power, right? So it's great because we understand everything about it, but it generates no power. Why? Because at some point it relies on some adiabatic process or some quasi-static exchange of energy. And why does it need to be quasi-static or adiabatic? Well, because you don't want to generate any entropy, right? So that's kind of a pity, because we get no power and very good, let's say, efficiency. And so now we would like to obviously get some power out of our device. So what do? We do the same thing again, right? The same sort of cycle as we were doing in our Carnot cycle, for example, but we just do it faster. In that sense, it's not quasi-static anymore, so we're generating some entropy, and therefore our efficiency is going down. So clearly the efficiency in all the devices is going down. Why? Because we have some diabatic process in our cycle now. And this diabatic process is generating some sort of entropy at some point. So my talk, even though you might not really recognize it during my talk, is exactly about this, about can we still do things fast, right? Which means I can transfer energy fast, so get power out, but avoid diabatic transitions. So that's where there's counter-diabatic driving. So can I counteract the diabatic effects? And if I'm efficient in counteracting these diabatic transitions, well, it means I'm reducing the entropy production, but still getting the same sort of power out. And so if you want to think in terms of efficiency, it's that, can I go beyond all these, let's say, maximal efficiency at maximal power results by basically, let's say, cheating and engineering a different Hamiltonian rather than running the same cycle as your normal Carnot cycle. So if you, this is just to set the scene, because it might look sort of different than what you know. And so, I mean, the basic example, and it will explain, I think, everything in this talk. And it's funny because both Anatoly and me, I think at some other conference, we woke up in the morning and we had a coffee and we came up with exactly the same example to explain our results in the morning. And it was like, there's this very extremely simple result you can use to explain everything. And it's the following. So imagine I'm a waiter, right? And my job as a waiter is to take stuff from the kitchen or from the bar and deliver it to the people in the restaurant or in the bar. So I'm holding a tray with a glass of water. And what is the universal way to deliver this glass of water? Well, it's adiabatic. It's quasi-static. That's how you do it. You go very, very slowly. You deliver it with no entropy production. It's perfect, but you're going incredibly slow. You get 0 tips. You make no money at all. Then what are you saying? Well, I want to make some, actually my boss is very unhappy with me because I'm delivering all the stuff extremely slow and customers are waiting, so I have to do this faster. So what do? You do it faster, and that's the problem, right? You do it faster, but at some point you're moving too fast and you're spilling everything, right? All the glasses are tipping over. But in this case, it's extremely simple. Everyone who's ever done this knows what to do. What to do is not to do the same protocol that you envisioned when you were doing it adiabatically or extremely slow. No, you modify the way you deliver the glass. And how do you do it? Well, you modify it by basically tilting your tray, compensating for the pseudo-force you generated by accelerating. And so by doing this, you can do it extremely fast. I mean, if you're good at this, in principle, you can do it as fast as you can run. Because if you're good at estimating your acceleration, if you just use the gravitational force to compensate for the acceleration when you move, you're exactly compensating for everything. And that means you can do this perfect quasi-static thing as fast as you would like. And so everything I will talk about today, if at some point you lose a thought of what is he talking about, try to think about this again, right? It's all about what do you have to do to efficiently implement the perfect quasi-static process, but as fast as you would like. And so this is like a waiter is doing essentially counter-diabatic driving. And so what I will try to explain is how do you do this for quantum systems? Yes?
And are you going to also explain, I don't know if the analogy is worth it for later on, but why it's not perfect? The fact that you're doing rotational acceleration, which means you're probably also generating some entropy, your glass velocity.
So I'll explain the difference. So there's actually, the reason Anatoly and me were so excited is that this is actually already a little bit cheating. And the cheating is exactly in the fact that the tilting is implementing something slightly different from what you would actually want to do. Yes. And so the point, and this I will stress maybe also now since you just asked it, is that, of course, if you would actually, so I'll show you the theoretical tools to exactly, for a glass, if you wanted to, compute this effective counter-diabatic drive, you would need to apply. And I will show you that actually it's exponentially complicated for this glass of water. Why? Because this glass of water is an ergodic system. It's chaotic. It's very complicated. But yet, this task of moving the glass is very easy in a sense. Why? Because I obviously don't care about keeping all the molecules in the water in exactly their ground state. I only care about not spilling the water, right? And so that's where the sort of cheating comes in, but that's also what saves us. So what is going to save us in the end for, let's say, chaotic or ergodic quantum systems is that this exact counter-diabatic drive, which wouldn't produce, let's say, any entropy, it's exponentially complicated to implement. But I will show you a technique which we developed that actually allows you to come up with extremely good approximations for this drive. So I hope this sort of sets the... I mean, I could stop my talk right now, actually. So to explain what we've been doing, I'll first try to explain what's non-adiabatic response. So I'll try to mathematically formalize this spilling of the water when you move too fast. And as you'll see, there's some concept of quantum geometry that come in. And so this links also different sort of fields. Then I'll explain you this counter-diabatic driving. And essentially, in coherent closed quantum systems, you can relate the ultimate speed at which you can do it to the so-called quantum speed limit. Because obviously, if you have even a closed quantum system, you really can't beat Heisenberg, right? That would be crazy. And then in the end, I will try to explain a way, so that's what we basically worked on, that we figured out a variational sort of approximation to compute these counter-diabatic drives. And then I'll show you various results on free fermions and chaotic spin chains to hopefully convince you that this is a nice technique. And so I hope I can convince some experimentalists to maybe use it, and some theorists that this is also a nice tool to actually get insight into physics of problems. So again, maybe slight motivation. You can pick any problem you like, but sort of our motivation comes not really from thermodynamics, but mostly from quantum mechanics. But as we all know, I mean, whether you talk about information or entropy, it's all the same. So you can envision that your application could be, instead of a heat engine, could be some quantum annealer like this thing, even though it doesn't work. But so, and you have some very complicated spin chain model, which has some easing model with certain types of coupling, and you want to change this coupling H. And by changing this H from, let's say, 1 to 0, you can anneal from some, let's say, polarized state in the X field, which is trivial to prepare, into hopefully some complicated ground state of some satisfiability problem, for example, that you wouldn't be able to compute the answer to. And so what's the problem in these machines? I guess you all know the story. It's that when I anneal, at some point I will encounter some extremely small gap in my spectrum. This gap sets the time scale I can use to change my magnetic field H. And so essentially, it turns out that you need to be exponentially slow to do this process in a complicated problem. And so we're again back to our Carnot problem. It's that if we want to do this efficiently, it needs to be adiabatic. But adiabatic could mean terribly slow. And so can we figure out a way to, just like in the waiter, to add some things to this Hamiltonian that slightly modify it so that I can implement this tilting of the glass on this D-wave machine, therefore implement the adiabatic thing, but in a reasonable sort of time. And so just to give you one example, let's say the first example, which I hope is understandable, it's like, okay, let's formalize this waiter sort of problem, right? So imagine now it's not a waiter, but maybe it's a tweezer. Right, and in the tweezer, so it's some optical tweezer with some shape like this, and maybe so the Hamiltonian is very simple. It's just one particle in this tweezer, and so what I can do is I can move this tweezer around. Right, so that's this lambda is the parameter that I can control externally. And so again, I want to analyze the corrections around the adiabatic limit. So we all know the adiabatic theorem, that if I do this extremely slowly, I'm guaranteed, if the system is gapped, that if I start in the ground state, that I stay in the ground state, right? And so to formalize this mathematically, it's very nice to do a unitary transformation, right? It's quantum mechanics, so I can work in any frame I like. So let's do some unitary transformation, u of lambda, which brings me, well, in general, I can take any unitary transformation. So let's do some unitary u, which depends potentially on lambda. So I mean, I satisfy the Schrödinger equation. So if I do this unitary transformation to this new frame, the new wave function satisfies the Schrödinger equation again, right? But with a different Hamiltonian, right? It's the unitarily transformed Hamiltonian. But that's not it, right? There's an additional term, which is, well, if your unitary does not depend on time, that's all you get. But if your unitary is time dependent, of course, from this dt, if you apply this unitary, you get a time derivative of this unitary in your new Hamiltonian. And so if we do this for this problem, let's imagine the unitary we do is the unitary that instantaneously brings us to the diagonal frame here. Well, I mean, what the unitary is doing, it's shifting this potential to the origin all the time. So what's the unitary that generates translations in space? Well, it's p2 times lambda, right? So if I take the derivative of this, well, I of course get lambda dot, how fast I'm changing the position of the tweezer, times the momentum operator. And that's logical because the momentum operator is the generator of translations, right? And so in the moving frame, so the frame that's moving with the tweezer, or in which the tweezer is always in the origin, right? The effective Hamiltonian is not just this Hamiltonian, but it's this. And so now you see that where does the adiabatic theorem come from? It's very simple in this moving frame. It's that if you're infinitely slow, the velocity is 0, I can drop this term, and I'm instantaneously diagonal. So obviously, I'm not generating any diabatic transitions. Well, you can, in this case, do one more trick, right? And that's you have lambda dot times p, so you can complete the square in this p squared, do some normal gauge transformation, right? You can turn this vector potential into a scalar potential because it's curl-free. And so you get m times lambda double dot times x. Yeah, and this is what we all know, right? That's Einstein's elevator problem, right? It's that, of course, you're in a frame that potentially accelerates. So your effective Hamiltonian is not just a bare Hamiltonian. There's a pseudo force to this Hamiltonian, which is, of course, proportional to the acceleration of your frame. But you see, this is what it is for this tweezer. We all understand it. It's like the waiter. But you can do this in general, right? I have any Hamiltonian, which depends on any set of parameters lambda. I can do this transformation u that brings me to the diagonal eigenbasis of the problem. I can define this object, which is now called not just the momentum operator, but it's actually the adiabatic gauge potential. So it's just a name. If you don't like the name, you can change it. It will become clear why I'm using the notation A in a second. And in my moving frame, I get a new Hamiltonian, which is the diagonal Hamiltonian minus some velocity times this field A. And so, well, why am I calling it adiabatic gauge potential? It's always sort of confusing people. Well, the reason I'm calling it like this is because, well, let's just check, do we know this object, right? So actually, we do know this object because this is an operator A. But if I would actually take the expectation value of this operator A in, for example, the ground state of the problem, this is nothing but the Berry connection. So if you're interested in sort of topological properties of systems, the expectation value of this thing is the geometric phase. But in general, this thing is an operator, and not just an expectation value. I mean, just to be complete, since this expectation value is the Berry connection, you can compute the Berry curvature like this. So this is the antisymmetric part of the correlator. And the symmetric part of the correlator is the so-called Fubini study metric. And so this defines a metric, essentially, on your ground state manifold of quantum states, if you would be in the ground state. And it's very nice because actually this metric has very nice properties, especially in quantum systems when they become universal. So for example, if you would have a second-order critical point, this has some nice universal scaling behavior. And again, so now you could actually see why this metric will turn out to be extremely important to define what is adiabatic and what is non-adiabatic, because essentially you have to move slow, but slow with respect to what, right? Or distance with respect to which metric? Well, this metric. And so now you see why it's hard to cross critical points, because this metric is diverging. So the smallest step you take is actually very large in the natural metric on these states of ground states. So before we go on, let's now see, well, what's this non-adiabatic response, right? I want to remove the non-adiabaticity because I'm changing my parameters too quickly. So, I mean, one thing we can do is what we all learned to do is let's just first do perturbation theory, right? I have some Hamiltonian. I know I'm essentially in the ground state of this part of the Hamiltonian. So let me just do perturbation theory with respect to this lambda dot times A. Because I'm relatively slow, I'm close to the adiabatic limit, I should be able to do perturbation theory because my perturbation theory is controlled by this thing. So even though my real perturbation might be large, the actual perturbation is controlled by the speed now. And so if the speed is slow, I can do this. And so what's the first order correction? Well, it's the geometric phase, right? The expectation value of this is just the expectation value of A, and so this is the Berry connection. And so you see, this first order correction as a non-adiabatic response is just a contribution to the phase of your wave function coming from the Berry connection. And so as long as you have a non-topological problem, you can remove this phase in principle because it's arbitrary. But if you have some topological problem, you cannot just arbitrarily remove this.
I mean, delta E1 is still dependent on time, so how to solve delta E?
Well, so delta E can depend on time t, right? I'm just doing perturbation theory, assuming that I'm in the state 0. So I could do, let's say, time-dependent perturbation theory in this case.
Time-dependent phase. Is it to gauge out?
Yeah. So that, I mean, in general, you can just remove this phase if you want, unless, of course, unless the Berry curvature is non-trivial, then you cannot. Right, so that's the thing. And you see, this depends on 2 indices, and that's why it might have a curl, and so you cannot just remove this quantity. Otherwise, you can remove it by just time-dependently shifting the energy. So we can look at the second order. So what was this in our case of translation? Yeah, clearly there's nothing special about this problem. So I mean, in this case, it's just 0. Because the expectation value of the momentum operator in equilibrium in my tweezer would just be 0. So now comes the interesting part. I don't have to stop, right, at the first order in the velocity. I can just go to second order or whatever order I like. And so if I go to second order, for example, then, well, I just do second order perturbation theory, nothing special. So I get a velocity squared term, energy denominator, and this matrix element between the ground state in this case and some excited state n. And so in general, it sort of looks like this. But now let's compute this quantity, right? So in the case of our tweezer, it's actually relatively simple to compute because imagine it would just be a harmonic oscillator, right? Then, I mean, the ground state, well, P is a dagger minus A. So you go to the first excited state, right? That's the only thing you can couple to. You square it. You put this in this denominator. If you sum over all these terms, actually what you get is that this term is proportional to lambda dot squared, right? So the velocity at which you change the tweezer. You pick up the mass, actually, of the particle inside the tweezer divided by 2. But what is this thing? Well, it is the additional kinetic energy, right, with a minus sign, associated with the fact that you're changing the tweezer. So it means, right, that since you were at energy, let's say 0, right, which you thought was the ground state of the problem, right, because you were in the ground state of this Hamiltonian, the actual ground state of the problem in second order perturbation theory is lower. Right? So there's some binding energy, which is given by m times lambda dot squared divided by 2. Well, but this is actually only saying that if I have a tweezer and I'm moving it with a certain velocity v, and there's a particle with a mass m inside this tweezer, yeah, obviously I have to carry the mass of the particle, right? It would be magic if I have a box filled with stones and the only mass I have to carry is the mass of the box. Yeah, obviously I have to carry the stones inside the box, right? That's this contribution. But this is also the contribution that's actually causing all the diabatic transitions. And so I hope this sort of sets the scene for what I'm about to do. So, well, now that we know how to analyze in a simple way how diabatic transitions are caused by changing some external parameter actually too quickly, how do I combat these transitions? Well, it's pretty easy actually, because, well, everything is caused by this term, right? Because this is diagonal. Also, if I allow myself to just add this term to my problem, I'm canceling it. So I'm left with my Hamiltonian, which is instantaneously diagonal, which is the thing I would be doing if I would be going infinitely slow. So if I define, and so that's called the counter-diabatic Hamiltonian, if I define the counter-diabatic Hamiltonian as my original Hamiltonian plus velocity times this gauge field A, essentially I'm guaranteed at that point that if I start in some eigenstate of this Hamiltonian H, no matter how fast I'm changing my parameters, I'm always staying in the instantaneous eigenstate of this Hamiltonian. Why? Because this is removing all diabatic transitions. And so now you could, of course, see that the faster you do it, the bigger this term will be. The more complicated the model is, right, the bigger the norm, for example, of this operator will be. Just like I told you before, right, the expectation value of the square of this operator was this metric tensor, and it was diverging at the critical point, which is saying that it's pretty hard to implement this sort of term when it becomes a complicated system. So one more trick you could play, exactly the same trick I was playing with the waiter or the tweezer, is that, well, you don't really have to implement this term because it might be hard. It's quantum mechanics, so I'm always allowed to do any sort of additional fictitious frame transformation, right? That doesn't mean that you have to implement this frame transformation in your lab, but me, as a theorist, can do all kinds of funky transformations. So, let me allow myself to just do some arbitrary unitary R on this Hamiltonian here. And so, what do I mean? Well, I just mean this, right? If you cannot, so to implement the counter-diabatic drive for this tweezer, what do you have to do? Add plus lambda dot p, right? But this might be hard, because how are you going to implement in your lab the momentum operator? It could be pretty hard, but actually, you don't really need to, just like the waiter doesn't do it, because the waiter actually implements this. It's a force, which is pretty easy to do, right? Much easier than this lambda, but these two are connected by this additional unitary transformation, which I here call R. And so if you can find this unitary R, there's one game we've recently been playing, which is you first figure out what this is, then you ask yourself, is there a unitary R such that this HFF, which stands for fast forward, because it's like you're fast forwarding your time evolution, that this HFF is the same as H, right? But with modified lambda tildes. Because if you can play this game, then you don't even need additional controls. You can have the original controls, you apply this, you gauge it away, you get the same Hamiltonian back. And so we have at least 3 or 5 examples where we can play this game very nicely. So, just to acknowledge, I didn't invent this gauge potential thing. So I think original work in totally different language was by Demirplak and Dries, which are chemists, quantum chemists. And then Barry independently did some work, obviously, because you see now why it's called A. It's related to the Barry connection. And then these gentlemen also worked a lot on this problem. So, just to give you an example of why am I talking about this tweezer problem, right? Well, just because this work is there. So it's a work from 2016 in which they basically made a game for people to play. So the game's called Quantum Move. And what people have to do is exactly this. So there's an atom inside a tweezer. They have to move this tweezer, pick it up, move it back. So it's like the problem we were considering, right? But this paper contains some sort of claim in which they say that people are extremely good at this because gamers have some brain power that is inaccessible to machines. And so they were able to outperform any quantum optimal control algorithm. And so I was like, that's kind of curious, because it seems that this is just this sort of waiter problem that we cooked up as a toy example. So, let's therefore just do it, right? So in this case, you have to do a slight modification because since there's 2 tweezers, this frame transformation isn't really a shift because that would also shift the second tweezer, right, which you don't have any access to. So the way to fix it is to actually say, well, let me do a general A, which is still generated by this shift, but it could depend on, well, this typo, it could depend on V of X and lambda. And then I just have to figure out the optimal, let's say, velocity field, V. But then you see the same sort of game can be done. I could actually gauge transform this thing back into the original Hamiltonian. And then you could actually see it's almost like a, so that's this, right? What happens if you move it too fast? Well, at some point you're moving it so fast that the atoms escape. So that's why you can't do arbitrary fast protocols. But you're also shifting the minimum of this tweezer, right? And so if I can undo this shifting of the minimum of this tweezer, I'm automatically adiabatic, right? And so, I mean, if we just apply this to this problem, so this is a plot which so this is stolen from this paper. This is what all the gamers did. So those are all the dots of all the statistics of all these people playing the game. This is their best optimal control result. And so with this counter-diabatic driving, I can just get an analytic formula of what the best thing is you should be able to get. That's this green line. And so then if I do this counter-diabatic driving, I get this blue result, which seems to be pretty much 50% fidelity around the time where I classically estimate that the particle would fly out. So you see, it's vastly outperforming all the humongous brain power of the gamers by just doing some physics. So maybe this is one application, right? So the reason this is really sort of something you would want to do if you have trapped ions or something, move these things around. So you can solve this problem with counter-diabatic driving. But you could argue, in this case, I mean, I didn't need all this theory about counter-diabatic driving to figure this out, right? So what about many-body systems, right? Can we do something on many-body systems? Well, it's a whole other ball game, I can tell you this, because the reason is the following. So, okay, so if I have this operator A, well, I can put in squeeze it between two eigenstates, n and m, which are instantaneously diagonal. Well, I can just compute, because this is a unitary that brings you to the instantaneous frame. So actually, if I solve this problem, what do I get? It's like the change of my Hamiltonian is the numerator, and then the denominator is given by this difference in energies. But now you see what the problem is. If we have an ergodic system, then actually the problem is that this denominator is exponentially small, and the numerator is also exponentially small. So S is the entropy. But not small enough, because this only goes like e to the entropy divided by 2, while this denominator goes like the density of states, so inverse density of states, so it goes like e to the minus s, which means that this matrix element is exponentially large. And so there's no way to do this in a chaotic problem, right? It's exponentially growing.
You have a typo there. E minus.
Yeah. There's a typo for sure. There should be a minus there, obvious. Otherwise, it would be even bigger. Yeah. So the thing is, this is very small, but this is even smaller. And so what's the difference between our simple integrable problems and non-integrable ones? Well, this denominator is still the same. You still get exponential density of states. But the thing is that there's lots of matrix elements which are exactly 0. And so all the states close by, which cause this problem, you get 0 matrix elements. So they're actually not a problem at all. And so what do we do? And I think, maybe then it's time to almost finish. What do we do, right? Is all that I've been telling you completely useless if you have a complicated problem? Well, it turns out you don't, because there's a clever trick. So, if this is true, then I can rewrite this expression by bringing this to the left side. Then you see I get matrix elements on all sides, so I can remove it, get an operator equation, which looks like the lambda h plus this has to be the Born-Oppenheimer force, essentially. So if I take the commutator, since this is diagonal, this has to be 0. So if I solve this equation, I actually solve this. It's a 1-to-1 correspondence. Well, And so now that's what we actually did. So if you want to figure out more, you should check the paper, obviously. But this, since it has like a double commutator, which is like a second derivative sort of problem, you would think you can always find some action, such that this is the Euler-Lagrange equation of some action. And this turns out to be true, so this is the action. And now if you minimize this quantity, of course, you're getting the exact solution back. But since you now have this minimal principle, you can just minimize it over some manifold of reasonable operators. And so that's, I won't go into the details, but that's exactly what you can do. It's like now you can put in any operator you can implement in the lab, minimize this action with respect to this operator, and get sort of the best approximation for your counter-diabatic drive. And I guess that's where I stop.